All brush arms are mounted onto the yoke, or sometimes called the rocker ring, and that's what's used to align all brush arms to the exact neutral position. Sometimes motor shops create a match mark between the yoke and the stationary bracket, and this match mark is in this picture. It's hard to see, but you can see there might be multiple marks. Well, which one's correct? There are several methods used for setting the brushes to the precise neutral position. Here are the three most commonly used. AC null method. It's used in the shop prior to doing a bidirectional. It can be used in the field, but we're going to explain why you wouldn't always do that. AC curve method, used initially in the shop prior to bidirectional as well. It's a more accurate method for setting neutral, precision neutral. And then the bidirectional speed method. It's very accurate. It's done in the shop. It's using sets the motor on a dyno and it rotates the motor under load in both directions. It obtains the same speed in both directions, reversing the armature current while the field stays the same. It's not practical to do that method in the field, but that's the most accurate method that we should be requiring of our motors prior to leaving the motor shop. About one method, the null method. First, we're going to seat all the brushes, connect 120 volt AC through a GFCI to the shunt field circuit, and connecting an AC source provides changing flux field across all armature coils. That will induce a voltage into those coils. We cannot source with DC current as in the case when the motor is operating. During operation, the changing field flux occurs due to the coils moving in the field. Without the armature rotating, there will be no induced voltage unless we make the shunt field the flux that's changing. We'll be measuring voltage that is induced across two adjacent brush arms, which is the voltage drop across all parallel paths. When set properly, the motor has excellent symmetry. The voltage would be zero or very, very close to zero. So we'll go through the AC null method first. You excite the field with AC. Then you're going to measure across the brush arms, rotate the armature for a minimum reading, and then adjust the yoke for a zero reading or as close to zero as possible. Moving the armature for a low reading, then we'll move the brushes for a zero if possible. Again, rotate the armature until we get as low a reading as we could, and then move the brush arms until a zero reading is accomplished. Another method is the AC curve method. It's a graphical representation of the induced voltage across several coils that span under the brush. First, we calculate the coil span by dividing the number of bars by the number of poles. And we'll be taking voltage measurements across 5 coils that pass under the brush. Now we're going to do that with these brushes lifted. We're not going to leave these brushes down as we did with the null method. We'll plot the measurements to determine the true neutral based on the graph. And to relate that to the brush position to the graph, we'll place the center of the brush at the slot between bar 2 and 3, shown on our graph. We then excite the fields with AC and take 5 measurements. We can enter these 5 measurements into the spreadsheet and then plot our curve. Notice the brush has been positioned at the middle between bar 2 and 3, and that's how the commutator is positioned when we took the measurements. We can now relate our measurements to the physical position of the brush. The curve should cross zero at the center of our brush. If not, we would adjust the yoke and try again. Now this method is more accurate than the null method. Following this, we would conduct a bidirectional test to confirm the neutral stays when armature current is present. This static test with the null or the curve method, AC curve method, is not done when there's any armature current, of course. It's not running. It's done static. Therefore, we have not got the interpoles or armature reactance in play at all. So the bidirectional will have those in play, and that will be the most accurate method to verify and check and set our neutral. When using the bidirectional load test method for adjusting neutral, the motor is connected to a dyno which can vary the load to the motor shaft. The test involves identifying the speed the motor runs in both directions while rated volts, full armature current, and full field flux, which is base speed. A motor is said to be correctly adjusted when it runs within 3 RPM in each direction at full load amps. The difference in this method versus the AC curve method is the fact that the armature current is flowing. With actual armature current flowing, the commutating poles and, if existing, compensating and series windings are also being tested. It is my opinion the motor's symmetry is in excellent condition when precise neutral, as derived in the AC curve method, agrees with the bidirectional load test. That doesn't mean a motor that is different between test methods is bad. However, the results of the dyno test should agree with the nameplate ratings. If symmetry is bad enough, the motor will not perform at nameplate ratings. This is done when a close examination of differences is necessary. Do you want a motor that has had a field pole rewind produce less horsepower or speed than before the rewind? The motor shop and the customer should discuss these differences, if there are any, to determine course of action, if any. In the example, the motor ran within 2 RPMs while at rated armature volts, armature current, and field current. The horsepower produced was very close to the nameplate horsepower rating. In this example, the nameplate RPM is slightly lower than the actual measured RPM. This can occur when the motor shop field current is somewhat inaccurate. When this does occur, the motor shop may need to verify their field current measurement equipment.